Dear students, in today's session, I'm going to explain important points related to chapter Electric Charges and Fields. Now this chapter is very important for all the competitive exams. So let's discuss the various formulas related to this chapter. The total charge on a body is given by the formula Q is equal to plus or minus NE, where N is the number of electrons lost by a body or gained by a body, where E is the magnitude of the charge of the electron. Now, the mass lost during charging or mass gain during the charging is given by M is equal to the number of electrons transferred from one body to the other body into mass of the electron, where Me is a mass of one electron, which is 9.1 into 10 to the power minus 31 kg. Now 1 coulomb is equivalent of 6.25 into 10 to the power 18 electrons. 1 coulomb is equivalent to 6.25 into 10 to the power 18 electrons. The ratio of the charge to the mass is called as the specific charge, which has a SI unit of coulomb per kg, and the dimensional formula of the specific charge is, for coulomb we write AT, that is ampere into time, that's AT, and for mass we write M. So when the term M is taken to the numerator, we will get ATM to the power minus 1. Now that is the dimensional formula of the specific charge. The force between two static point charges Q1 and Q2 separated by distance r in vacuum is given by F is equal to 1 by 4 pi epsilon naught into Q1 Q2 by r square. But in a dielectric medium, Fm, this is F suffix A, is equal to 1 by 4 pi epsilon naught epsilon r into Q1 Q2 by r square. The value 1 by 4 pi epsilon naught is 9 into 10 to the power 9, and the value of the dielectric constant epsilon r, the least value is 1 for vacuum and the highest value is infinity for a conductor. If part of the space is filled with a dielectric medium of dielectric constant epsilon r having thickness T, and if r is the separation between the two charges, then the force between the two charges is given by 1 by 4 pi epsilon naught product of the charges Q1 Q2 divided by the thickness of the dielectric medium, which is the T, square root of the dielectric constant, which is epsilon naught, plus the thickness of the air space, which is r minus T, the whole square. So that's the formula used to find the force between two charges when part of the dielectric is filled between the two charges. Dielectric constant is also defined as the ratio of force between the two charges in air to that of the force between the same two charges in the medium. And dielectric constant is also given by the ratio of the absolute permittivity of the medium to the permittivity of free space, which is epsilon naught. So these are the equations based on the Coulomb's inverse square law, and they are important to find the force between two point charges separated by a certain distance, either in air or even in vacuum. When a body is charged, the distribution of the charge on such bodies, it depends on the shape of the body. It depends on the shape of the body. In the case of linear conductor, straight wire, thin wire, we measure linear density of the charge, which is denoted by lambda, and is given by charge per unit length. They find it that is coulomb per meter. That's in the case of linear conductor, and we measure linear density of charge. In the case of conductor of any shape, we measure surface density of charge, which is sigma, which is the charge per unit area, and the unit is the coulomb per meter square. And in the case of non-conductor, we measure volume density, rho, that's equal to charge per unit volume, which is coulomb per meter cube. So for linear conductor or for a straight wire, we use linear density of charge. For only conductor or any shape, we measure surface density of charge, and then in the case of non-conductor, we measure volume density of charge, denoted by rho. For charge spherical conductor, the surface density is given by Q by 4 pi r square, where r is the radius of the sphere and Q is the charge distributed uniformly over the sphere. Now, the surface density of charge is always inversely proportional to the radius of curvature. Lesser the radius of curvature, more is the concentration of the charge, or more is the surface density of the charge. If I consider two charged spheres, two charged sphere plus Q and plus Q. When they are charged, they repel to a certain distance. Distance is R, and the length of the string is L, and the angle made by each string with a vertical is a theta. The reason why they repel each other is because of the electrostatic force of repulsion, which is F. And because of the mass, there is another force which is acting, which is in the downward direction, which is mg. And along the string we have a force which is tension, so that each sphere is under the action of three forces: weight, electrostatic force of repulsion, and the tension. So that what is the relation between the three forces when they are in equilibrium? So we can find tan theta, the theta's angle made with the vertical. Tan theta is equal to F by mg, or F by w, where F is the force between the two charges, which is 1 by 4 pi epsilon naught. Product of the charges is q square, and square of the separation between them. Now that is F. And W is equal to mg. Now since this sphere is in equilibrium, the net force is 0. Therefore, the tension T is equal to square root of F square plus W square. So using these equations, we can find any of the variable, the angle made by the string with the vertical, the force between the two charges, even the charges on both the sphere, as well as the tension in that particular spring can be calculated, provided the two spheres are in equilibrium. The space around a mass is called as the region of gravitational fields. Similarly, space around a charge is called as the region of electric field. And the strength of the electric field due to a charge, the distance r, can be calculated using E is equal to 1 by 4 pi epsilon naught q by r square. And this field has two units, one Newton per coulomb, the other volt per meter. And the direction E is a vector. The direction of this vector depends on the nature of the charge. If the charge is positive, the direction of the field is away from it. And if the charge is positive, it's away from this charge. And if the charge is negative, then the field at that particular point is towards that charge. The magnitude of the field, it remains same in both the cases. At the same point, we can even measure the electric potential. So what is the electric potential at these points? It's given by V is equal to 1 by 4 pi epsilon naught Q by R. So that E and B are related by E is equal to V by R. Electric potential is a scalar. So therefore it is a positive in the case of positive charge and it is a negative in the case of negative charge. And in a medium, the electric field and the electric potential changes like this. E is equal to 1 by 4 pi epsilon naught epsilon R into Q by R square. So we need to introduce the constant associated with the electric field. Similarly, the potential V is equal to 1 by 4 pi epsilon naught epsilon R into Q by R. So these are the equations for electric field and electric potential in vacuum, and these are the equations for electric field and electric potential in a dielectric medium due to a point charge. And more important, electric field is a vector quantity, electric potential is a scalar quantity. If there are system of charges, many charges, Q1, Q2, Q3 and so on, many charges. How do we find the net field due to all these three charges? So we use the principle of superposition where the resultant electric field is equal to vector sum of the electric field due to the individual charges. So we use this formula to find the electric field due to system of charges. How to find the net potential at that point? The net potential is equal to the algebraic sum of the potential due to individual charges. So net electric field due to the vector sum of the individual electric field, and net potential is equal to the algebraic sum of the potential due to every charges. A pair of equal and opposite charges, point charges, separated by a distance of 2a, is called an electric dipole. A pair of equal and opposite point charges separated by a certain distance is called as electric dipole. The strength of the dipole to produce electric field can be expressed in terms of a physical quantity called electric dipole moment, which is denoted by P, and that is equal to, it's a Q into 2a, Q into 2p, where Q is the magnitude of either of the charges and 2a is called the dipole moment. And it's a vector quantity, it's always directed from negative to positive charge. The line passing through the 2 point charges is called as the axis of the dipole, and the line perpendicular to that passing through the center is called as a perpendicular bisector. It's called perpendicular bisector. On the axis as well as on the perpendicular bisector, it produces electric field as well as electric potential. So what is the electric field at a point on the axis? What is the electric field at a point on the perpendicular bisector? The net electric field at a point on the axis is E is equal to 1 by 4 pi epsilon naught 2pr by r square minus a square the whole square. Whereas at a point on the perpendicular bisector, E is equal to 1 by 4 pi epsilon naught p by r square plus a square to the power 3 by 2. So these are the electric field at a point on the axis, and this is the electric field at a point on the perpendicular bisector. Now what is the direction of this? At a point on the axis, it is along the direction of the dipole moment. Whereas at the point on the perpendicular bisector, it is parallel to the axis but opposite to the direction of the dipole moment. Exactly opposite to the direction of the dipole moment. If the distance that is taken at a point on the axis, which is normally taken as r, is much greater than the semi-dipole length, which is A. And such a dipole is called short electric dipole. At any point, what is the electric field due to a short electric dipole? What is the electric potential due to short electric dipole? So E is given by 1 by 4 pi epsilon naught P into root of 3 cos square theta plus 1 by r cube. Whereas the potential is given by V is equal to 1 by 4 pi epsilon naught P cos theta by r square. So this is the expression for electric field at any point due to a short electric dipole. Expression for electric potential at any point due to a short electric dipole, where theta is the angle made. For example, if this is the point, the distance r, then theta is the angle made by the line joining the point to the center with the axis. So that is theta. Now, if the point is on the actual line, then theta is 0. On substituting 0 here, you will get the electric field E to be equal to 1 by 4 pi epsilon naught cos 0, 1, 3 plus 1, 4, and with the root, you will get 2, so that's 2p by r. If the point is on the perpendicular bisector, theta is 90, so this term becomes 0. So you get E is equal to 1 by 4 pi epsilon naught p by r. Similarly, the potential at a point on the axis, theta 0, cos 0, 1, you will get V is equal to 1 by 4 pi epsilon naught p by r square. But if I take point on the perpendicular bisector, theta is 90, you will get V 0. That means the potential is 0 at each and every point on the perpendicular bisector. So these are the comparative equations pertaining to a short electric dipole, where the first column gives electric field and the other column gives the electric potential due to short electric dipole only. If an electric dipole is placed in an electric field, this is the direction of the dipole moment, and theta is the angle between the dipole moment and the electric field. Then this dipole experiences force, both ends, that is the center of negative charge and the center of the positive charge, they experiences forces in this direction, due to which the entire dipole experiences a torque, and the torque is given by tau is equal to Pe sin theta. You can write this in vector form, that's vector tau is equal to vector P cross vector B. And if you want to rotate this dipole against this electric field, then you need to do some work, and that work has to be done, which is given by W is equal to Pe into 1 minus cos theta. And when we write this equation, we assume that the dipole is initially parallel to the direction of the electric field. That is also called as a stable equilibrium position. And whatever the work done in rotating the dipole is stored as an energy in the dipole, which is given by U is equal to minus Pe cos theta. And we can write that in vector form, which is U is equal to minus vector P dot vector B. And the various cases, if theta is equal to 0 degree, then sine 0 is 0, so torque is minimum, which is 0. When theta is 90 degree, sine 90 is 1, so torque is maximum, which is equal to P. And when theta is 180 degree, the torque again is a minimum, which is 0. So torque is a minimum when the dipole is either parallel or anti-parallel to the direction of the electric field. And when the torque is minimum, it's in the stable equilibrium position. And when theta is 180 degree, it's in the unstable equilibrium position. So what is the work done in rotating the dipole from stable equilibrium position to certain position? So again, when theta is 0, theta 0, cos 0, we'll get 1 here, correct? So therefore we'll get W is equal to 1 minus 1 becomes 0. When theta is 90, this term becomes 0, so we'll get W is equal to P. When theta is 180, cos 180 is minus 1, 1 minus of minus 1 is 2, so therefore W is equal to 2P. So that means when it's in the stable equilibrium position, we don't have to do any work. And to rotate through an angle of 90 degree, the work that has to be done is equal to P. And we have to do maximum work, which is W is equal to PE. Here when theta is 0, we get U is equal to minus P. Theta 90, U is equal to 0. And theta 180, U is equal to P. So the potential energy is least minimum, that's why the dipole is in stable equilibrium position. And when the potential energy is maximum, it's in the unstable equilibrium position. So these are the equations which are again important related to dipole when present in an uniform electric field. The next important concept is electric flux. The number of electric lines of force passing normally through a given surface is called as electric flux, and we can measure this electric flux. Delta phi is equal to E delta S cos theta, where E is the electric field and delta S is the area vector, which is always normal to the surface of the conductor, or normal to the surface of the area which we consider. Theta is the angle between electric field and the area vector, and it's measured in terms of an SI unit, which is volt meter. If you want to measure the total flux, then phi is equal to summation of E delta S cos theta. When we use the first equation, we measure the flux through a small surface. And the next equation is used to find the total flux through the entire surface. There is the electric field at each and every point on the surface. If the surface taken is a rectangular surface like this, and the area vector is always normal to the surface, so this is the area vector. If the field is also along the same direction, then the angle between the two vectors is 0, cos 0 is 1, we get maximum flux. So when theta is 0, the flux is maximum. Now if I consider surface, again of any shape, and if this is the direction of the electric field, the normal to the surface is the direction of the area vector. Area vector is always along the direction of normal to the surface. So now the angle between the area vector and the field is 90 degree, and when theta is 90, so we get minimum flux. Therefore, the flux is a minimum. So when the area vector is along the field, the flux is maximum, and when the area vector is perpendicular to the field, the flux is minimum. Flux is related to the electric field. electric field in turn depends on the charge. Therefore, the relation between the flux and the charge is given by an important theorem which is called the Gauss theorem. The Gauss theorem states that the total flux through a closed imaginary surface in vacuum is equal to 1 by epsilon naught times the total charge enclosed by the closed surface. The flux can also be measured as surface integral of the electric field gives the flux. So this is the surface integration. So surface integral of the electric field is equal to the flux. So that's why it is also equal to 1 by epsilon naught into Q enclosed. So this is the alternative way of writing the Gauss theorem. So where phi is the flux and this is the surface integral of the electric field, which is measure of the flux, and that is equal to 1 by epsilon naught times total charge enclosed by the closed surface. And that closed surface is an imaginary surface which can be of any shape, and that closed surface is called as the Gaussian surface. Now, using this Gauss theorem, we can find the flux through a cubical surface. So let this be a cubical surface, and I'm going to place the charges at the various points of the cubical surface. So this is the cubical surface. If the charge is at the center of the cubical surface, the charge is at the Q, is at the center, then what is the total flux through this entire cubical surface? So since the charge is at the center, the flux through this entire cubical surface is given by the Gauss theorem, which is phi is equal to Q by epsilon naught. So that is the total flux through the entire cubical surface. Now if they ask what is the flux through each phase, each phase when Q is at the center. The cube has total 6 phases, so therefore this is the total flux, and that flux is divided equally among all the 6 phases. So that's why the flux through each phase when Q is at the center is given by Q by 6 epsilon. Q by 6 epsilon. So I'm going to remove this charge and I'm going to place it at one of the face. So face center. Now to find the flux when the charge is at one of the face is, I cannot apply the Gauss theorem straight away to this diagram or to this situation, because the charge is not enclosed by the cubical surface, it is on the surface of the cube. So therefore what you have to do is you need to assume one more identical cube on the right hand side of the system. Not one cube, assume one more imaginary cube on this side, on the right hand side. And when you do that, now that particular charge will be enclosed by 2 cubes together, and it will be inside the system, because to apply the Gauss theorem, we need to place the charge within the Gaussian surface, not on the surface. So now since it is enclosed within 2 cubical surfaces, the total flux through both the cube is Q by epsilon naught. Through both the cube, it is Q by epsilon naught. But we wanted flux through one cube, so that's why it is a Q by 2 epsilon naught is the flux when the charge is placed at the face center. Now, I'm going to place the charge now at the edge center. It's placed at the edge. Now, when it's placed at the edge of it, again, it's not enclosed by the entire cube. So that's why to enclose it, I have to assume 2 more cube above these 2. So first originally I have taken 1 cube, then I assume the 1 more to enclose the charge here. But now when I place it at the edge, to enclose that I have to assume 2 more cube above this. 1 here and 1 more here. And now you can see the charge displaced there is enclosed within 4 cubes. So what is the flux through the 4? It's a Q by epsilon naught. So what is the flux through each? It's Q by 4 epsilon. And the last, when the charge is placed at the corner, now I'm going to place it here, when the charge is placed at that corner. Now if I place the charge at that corner, then to enclose that, total I have to consider 8 cubes. So this is the corner if I place it. Then one cube here on the side. Then 1 cube on this side. And 1 more cube here. So this is 1, 2, 3, and 4. 4 cubes together. But even after taking 4 cubes, the charge is not enclosed within the system. So what I have to do is I have to take 4 more cubes above these 4. So that total cubes that encloses that charge are 8. So the flux through all the 8 cubes is Q by epsilon naught, and through each it is Q by 8 epsilon naught. Through the 8 it is Q by epsilon naught. Through each it is Q by 8 epsilon naught. So that is how we can find the flux through the cube when the charge are placed at different locations. Now one more question here, that is when the charge is placed at the corner, the 3 nearest faces to that charge, there is no flux. Which are those 3 nearest faces to that charge? So one is this. This is one of the faces. The other is here. And the next is the one which is here. So the lines of forces for all these 3 faces, lines of force, all these 3 faces, are parallel to the surface. That's why there is no flux through the faces nearest to those 3 surfaces. No flux. That means flux through the remaining three surfaces. See, total flux through this entire cube is Q by 8 epsilon naught. Total. Since it is shared by 3 more faces, the flux through 3 faces are Q by 24 epsilon naught. Because Q by 8 epsilon naught is shared by 3 more faces. So divide by 3. Q by 24 epsilon naught. So out of the 6 faces, 3 faces which are nearest to that charge we replace it. Okay? I'm going to mark here. So this is one surface through which there is no flux. This is the second surface through which there is no flux. And this is the third through which there is no flux. So that means there is flux through this surface 1 and 2, and here bottom which is 3. And what is the flux through those 3 surfaces? It is Q by 24 epsilon naught. What is the flux through the surfaces nearest to that charge? It's a 0. So this is one important concept of finding the flux when charges are placed at the different locations of a cubical Gaussian surface. Electric field at a point due to a charge is nothing but a force per unit charge gives electric field. Similarly, electric potential at a point is given by work done per unit charge. Potential is measured in terms of volt, whereas electric field is measured in terms of Newton per coulomb or volt per meter. So what is the relation between electric field and electric potential? If potential is given, then electric field is measured as negative potential gradient minus dV by dx. And electric field is a vector. Since it is along the x-axis, we can introduce I cap. If electric field has component along x, y and z, then we can write vector B is equal to minus dV by dx I cap minus dV by dy j cap minus dV by dz k cap. So that's the electric field, and these are the components of the field along x, y and z. So therefore this is equal to Ax I cap plus Ey j cap plus Ez k cap. That's E vector. Therefore the magnitude of the E is given by magnitude of the vector E is given by root of Ex square plus Ey square plus Ez square. With the help of potential, we can even measure the work done. Work done is equal to the charge moved into the potential difference, which is VA minus V. So this is the work done in moving a charge Q0 from B to A. From B to A. What is the work done in moving the charge from A to B? It's a Q0 into VB minus VA. If potential is given, then we find negative potential in the gradient. That means we differentiate V with respect to x. Then we find electric field. If electric field is given, how to find the potential? So potential difference VA minus VB is equal to negative integration of vector E dot vector dr, within the limits A to B. So if potential is given, to find the field, differentiate the potential with respect to the function or variable. And if electric field is given, if you want to find the potential, then integrate that electric field with respect to R. So this is the way to find two quantities by knowing the other physical quantity. Electric field and electric potential. Electric field and electric potential. Due to charged spherical shell. Spherical shell. So charged spherical shell. Spherical, charged, and then shell. Shell means it's a hollow sphere. What is the electric field? Anywhere inside the sphere. Anywhere inside. Anywhere inside, it's given by 1 by 4 pi epsilon naught q by r square. Where r is the distance of the point from the center of the sphere. Potential is 1 by 4 pi epsilon naught q by r. Now that is potential. Sorry, it's not potential inside, this is potential outside outside. This is the potential outside. Now, what is the electric field on the surface? On the surface, it is 1 by 4 pi epsilon naught q by capital R square. And potential on the surface is 1 by 4 pi epsilon naught q by capital R, which we can even write as sigma by epsilon. Sigma by epsilon. So here, sigma R by epsilon. In all these formulas, we can always replace Q as sigma into 4 by R square. Charge Q is equal to sigma into 4 by R square. Sigma is surface density of charge, R is the radius of the sphere, and Q is the charge distributed uniformly over the surface. Now, what is the field inside? Field inside is 0. What is the potential inside? Not 0. That is same as that on its surface. Then what is 0 inside? Only potential difference inside is 0. Potential difference is 0, not potential. So these variation of the field as well as the potential can be understood in terms of a graph. This is potential versus the distance. Electric field versus distance, potential versus distance. So inside it is 0. Anywhere inside the field is 0. And it's 0 till the surface, that means till we reach R is equal to R. And then on the surface the field is maximum. Then beyond the surface it varies inversely as R square. So this is E inversely as R square. So field becomes 0 only when R becomes infinity. Field vanishes only at infinity. And when we draw potential versus R, potential inside is same as that on the surface. It's a constant value. There is no variation. Constant. Till we reach the surface, till R becomes R, it's a constant. Then it decreases and it varies V inversely as R. V inversely as R. So this is how the potential decreases with respect to the distance. And again, only at infinity the potential becomes 0. So these are the graph that shows the variation of electric field and electric potential in case of charged spherical shell. And in all the equation, Q can be replaced as sigma into 4 pi R square. We can write equation pertaining to the electric field and electric potential due to charged spherical solid non-conductor. So uniformly charged sphere, it's a non-conductor and it is a solid. That means the charges are present even inside the sphere as well. So in this case, the electric field outside, is same as that in the case of spherical shell, which is 1 by 4 pi epsilon naught q by R square. Potential V is equal to 1 by 4 pi epsilon naught q by R. That's V outside. And electric field on the surface is same as that again in the previous case, which is 1 by 4 pi epsilon naught q by capital R square. Potential on the surface, again no change. 4 pi epsilon naught q by r. And here we can write rho is equal to, or q is equal to 4 by 3 pi r cube into rho. We can write q is equal to 4 by 3 pi r cube rho. So that's how we can write the charge. In all these cases, charge can be replaced in terms of volume density, because the charges are distributed even within the sphere. Now what is the electric field inside? It's not zero, which is 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, q into r by r cube. Potential inside 1 by 4 pi epsilon naught, it's a 3 r square minus small r square by 2 r cube. So that's the potential inside. Now what is the electric field at the center? This r is the distance of the point from the center. So therefore electric field at the center is 0, because r is 0. What is the electric potential at the center? When r is 0, you get r square by r, you will get r. So if it's 3 by 2, 1 by 4 pi epsilon q by capital R. And this value 1 by 4 pi epsilon q by r is nothing but same as that, the potential on the surface. So that's why it's also equal to 3 by 2 times the potential on the surface. So the potential at the center is equal to 3 by 2 times or 1.5 times potential at a point on the surface. So there's a slight variation in the equation of the electric field and electric potential due to charged spherical solid non-conductor. So what is the variation of the graph in these two cases? So that's what I'm going to explain based on the equation that we have written in. The variation of the electric field with the distance. Since E is directly proportional to R inside the solid conductor, E is a linear till the surface, till R becomes R. And beyond that, it varies inversely as R square. So E inversely as R square. So that's the graph of the electric field versus the distance. In the case of potential versus distance, at the center potential is constant, so not zero. So therefore, it decreases till it reaches the surface, R is equal to R. And beyond that, again, it varies inversely as R. So that is the graph of the electric field versus potential in the case of charged spherical solid non-conductor. The next charged body is uniformly charged ring. In the case of uniformly charged ring, let R be the radius of the ring, this is the axis of the ring, and we are going to consider a point at a distance x. The electric field at any point on the axis is 1 by 4 pi epsilon naught q into x by r square plus x square to the power 3 by 2. But the potential is V is equal to 1 by 4 pi epsilon naught q by r square plus x square to the power half. To the power half. Now, at the center, E at the center. So at the center x is 0. And when x is 0, we get 1 by 4 pi epsilon. Sorry, x becomes 0, so therefore field also becomes 0. We don't have to write the other terms. So electric field at the center is 0. But potential is not 0. It is given by V is equal to 1 by 4 pi epsilon naught Q by R, because x becomes 0 and R squared to the power half is R. So field is 0 but potential is not 0. If we take x, very large compared to R radius, this distance is much greater, then we have to neglect the value of R, and when we neglect the value of R, we get E is equal to 1 by 4 pi epsilon naught Q x here. R we are going to neglect, we are going to neglect R here. And in the denominator we get x cube and then this x. So we get Q by x squared. 1 by 4 pi epsilon naught Q by x squared. And in case of potential, we get V is equal to 1 by 4 pi epsilon naught. We have to neglect our x to the power half is nothing but only x, so that we get Q by x. So these are the expressions related to electric field and electric potential at a point on the axis of a uniformly charged ring of radius r, and x is the distance of the point from the center of the ring. So what is the expression for electric field due to a uniformly charged thin wire having lambda as the linear density, and then r is the perpendicular distance. So these are the ends joining the conductor, and electric field at this particular point is given by E is equal to 1 by 4 pi epsilon naught 2 lambda by r sine alpha by 2. We get sine alpha by 2, where alpha is this angle, total angle. So this angle is alpha. 2 lambda. Lambda is the linear density of the charge. Suppose if the wire is an infinitely long wire. If it is infinitely long wire, then this entire angle, this angle becomes very large, and it becomes almost 180 degree. And if I substitute that here, sine 180 by 2, sine 90, we get 1. So therefore, for infinitely long charge wire, we get E is equal to 1 by 4 pi epsilon naught 2 lambda by r, the expression in that. One more conductor we are going to consider, that is infinitely long, uniformly charged thin sheet. Infinitely long, uniformly charged thin sheet. So field around it at any point is given by E is equal to sigma by 2 epsilon, and is independent of the distance. So that means this field is uniform throughout in either direction. Sigma is the surface density of this thin charged sheet. If I consider two such sheets which are parallel to each other, that will give you, so this is one sheet of charge, and if we have one more sheet of charges, oppositely charged sheet. The first one is positively charged, the second one is negatively charged. Now what is the net electric field between and outside these two charge sheets? At a point outside, The electric field due to this positive charge will be away from it. This will be away. Due to this negative charge, it will be towards the negative charge. It will be like this. Same thing here. Due to this positive charge, away from it. Due to this negative charge, it's towards. And now these two fields, they have this magnitude, sigma by 2 epsilon, sigma by 2 epsilon. Here also sigma by 2 epsilon, sigma by 2 epsilon, and they get cancelled. So therefore the field becomes 0. What is the field here in between? The field in between, due to positive charge away from it, due to this negative charge it will be towards. So therefore two fields, they'll add up. So sigma by 2 epsilon plus sigma by 2 epsilon, and you get values. The field between is equal to sigma by epsilon naught. Therefore, the net electric field between two oppositely charged parallel plates is equal to sigma by epsilon naught, whereas the fields outside the two, it is 0. So that's the application of the electric field due to an infinitely long thin charge sheet of wire. So if I consider an arc which is charged uniformly, having linear density lambda, and if that arc subtends an angle, arc having radius r, and if it subtends an angle alpha, then lambda, where r is the radius, lambda is given. Lambda is equal to charge per unit length. So total charge I'm going to consider Q divided by arc length is nothing but r alpha, r into alpha. So this is the linear density of an arc. Now what is the electric field at this particular point? So E is equal to 1 by 4 pi epsilon naught 2 lambda by r into sine alpha by 2. Where lambda is the linear density of charge, which is given by Q by r alpha, where alpha is the angle subtended at the center by this particular arc. Now, if I consider a semicircular arc, what is the alpha if it is semicircular? If I extend it, it is semicircular. If it is semicircular, then alpha is 180 degree. So 180 by 2, 90, sine 90 is 1. So therefore you get expression for electric field at this particular point. E is equal to 1 by 4 pi epsilon naught 2 lambda by r. This is capital R. So that's the expression for electric field at the center of semicircular arc having radius r, and lambda is the linear density of the charge. Suppose if it is a straight conductor, then we write lambda is equal to Q by L. For straight conductor, lambda is equal to Q by L. But for the arc length, it is R into alpha. So we use arc length. S is equal to R theta. S is equal to R. R is the radius here, and theta is nothing but alpha. So that's why it's a Q by R alpha, the method by which we find the linear density of an arc. And this is the formula for electric field due to this entire arc. And if it is semicircular, then we have a special case where theta becomes 180 degree. So in one more session, I'm going to explain the remaining concept related to this particular